In Lab 4, we discussed oscillations. In this lab, we examined the motion of a spring mass system in which the mass swung in an arc while oscillating on a spring. We extracted position versus time data in both the x and y directions using Tracker, then wrote a program in GlowScript that we then compared to the experimental model. In addition to this, we modeled the change in energy throughout the system using our GlowScript code. Just like in previous labs, Newton's second law, which can be seen below, applies here. In Newton's second law, the final velocity of an object is equal to its initial velocity plus the net force acting on it, multiplied by the change in time. In this lab, we applied this in conjunction with spring force, which we can write as the force of spring is equal to the negative spring constant multiplied by the stretch or compression of the spring multiplied by L hat, which gives us our direction. We also could solve for different types of energy, including potential and kinetic. Kinetic is given by 1/2 the mass of the object times its velocity squared, and potential is given by mgh, where m is the mass of an object, g is the acceleration due to gravity, and height is the height of the object. The spring constant of our spring, as well as its relaxed length L0, were the same as those given in our edX videos, as the spring used was the same. However, the spring in the edX video only had a vertical component to its motion, while the video we analyzed had both horizontal and vertical components. Moving on to our code, we can see the things we edited in order to create a perfect system, or a system to model our experimental data. First, we had to set the ball's mass as the 0.402 kilograms given in the edX videos. This initial position was given by our data in Tracker, as well as the ball starting from rest. Our time started at 0 using a delta t constant that we chose in our data. The force of gravity is given as 9.8. The spring constant was same as our edX video, 6.83. Our relaxed length was 0.17 meters. And then, in order to specify the vector L, we used the ball's position minus the position of the spring. L hat, which gives us the direction, was L divided by the magnitude of L, and S, which gave us the compression or stretch of the spring, was the magnitude of L minus its initial length. Then, we solve for our different types of energy. Kinetic energy is given as 1/2 times the ball's mass times its velocity squared. Potential is given by mass times g times height, and spring energy can be given as 1/2 spring constant times s squared, where the total energy can be given as kinetic plus potential plus spring. Here, we had to calculate our vector forces. First, the force of gravity is given by the vector 0, negative m times 9.8, 0. The force of spring can be given as negative ks times s times L hat. The total net force can be given as force of gravity plus the force of the spring. And here, we apply the momentum principle, where we can do the final velocity of an object is equal to its initial velocity plus its net force divided by its mass times the change in time, where the net force divided by mass is equal to our acceleration. We can also update the position by giving the final position is equal to initial position plus velocity times time. Here, we use the same formula as above to update our spring. Finally, we calculate our changes in energy, where our formulas for energy, kinetic, potential, and spring are the same, except to solve for delta K, we use this energy minus its initial energy, final minus initial. As well as for the total energy, we use the final energy minus the initial energy. When we run our code and compare it to our initial model, we see several important things. First, the total energy throughout is 0, meaning that our energy principle was satisfied here. Then, we can see that in our x position data, our experimental model started very close to our theoretical model, and then as time increased, moved further and further away. When we move to our y position, we see that it was very similar all the way throughout the experiments. In this lab, we made several key assumptions that led to the discrepancies between our experimental and theoretical data. First, we had to assume that our data in Tracker was calibrated correctly. Small mistakes in the placement of our origin or length of our calibration stick could have made our data incorrect. Secondly, and most importantly, we had to assume that the spring itself had no mass. Real-world springs do have mass that affects them, but for the sake of this lab and most intro-physics problems, we consider the mass of the spring to be negligible. What does it mean? When we looked at our graph for our energies, we saw that the total energy remained at 0 throughout the experiment. Therefore, we know that the energy principle is satisfied, because throughout all the experiment, the spring energy, potential energy, and kinetic energy all sum to 0, and there was no transfer of energy through external forces. Using the data obtained in Tracker, We were supposed to make two separate estimates of oscillation periods, one from the x position and one from the y position. For both, we can look at our graphs and tracker and calculate that the period for the x direction was 1.519 seconds, and for the y direction, it was 1.425 seconds. These are different for the reason that there are different forces in different directions. In the y direction, we have to account for both the force of gravity and the force of the spring, meaning it oscillates at a faster rate than in the x direction.